Hello, and welcome to the Calorimetry Applied to Calculating Delta H of Reaction note session. The following would be helpful for you to have out. So in the Unit 5A notes, starting at the bottom of page number 11, and we're going to be going through page number 13 with some examples. So it'd be very helpful if you could work along with that. Okay, so far in this unit, if we remember, Unit 5A is all about how do we calculate and use delta H, which is enthalpy. And we remember this is not the same as temperature. This is the exchange of heat energy. So energy moving from one system to another system. So the transfer of energy. Okay. And so this entire principle applies the law of conservation of energy. So you're transferring heat energy from one system into another system. And so in this unit, we have learned that we can calculate delta H a number of different ways. So we can calculate it from an energy, an energy diagram. And all of these have previous sessions. Enthalpies of formation, bond enthalpies. You can also calculate it from heating curves, applying the MCAT and the heat of vaporization and of fusion. And we also can take a look at how heat can be transferred from one substance to another substance. And so these are all different things that we've already done in this unit. And you can go back and watch in previous episodes. This one is going to be focused on how do we unite calorimetry to solve so that heat exchange, to solve for delta H of a reaction. So not just to use tables, but to use experimental data in order to be able to solve for delta H of a reaction. So how much heat is exchanged per 1 mole of reaction. And so the challenge with this is that calorimetry relies on a specific equation. And that equation is that Q equals MCAT. That's one part that we rely on. Okay, and I want to talk about this first. So Q, we remember, is basically exchangeable with delta H. The two mean the same thing, so the transfer of heat energy. M as mass is the specific heat capacity, which is a constant that's given to you for each different substance. And the change in temperature is, so delta T is T final minus T initial. And you have to make sure that final comes first, or else your signs will be flipped. Though the problem for calculating Q for reaction is reactions don't have masses, and you can't measure the temperature of something if it's not a physical object. A reaction is a change in other objects, a total change of a system, but it's not actually physical objects. It requires physical objects, but the reaction in and of itself isn't a physical object. So then how can you have a mass for a reaction? You can't. You can't have a specific heat for a reaction. You can only have it for a substance. You can't have a temperature change for a reaction. All of these things have to be measured in a substance. And so this is where the other component of calorimetry is going to come in. And that is what tells us that the positive Q endo is equal to the negative Q for the exo. So the thing that is absorbing the heat got it from the thing that released the heat. So the thing that released the heat gives it to this thing which absorbs the heat, or it could even be that the thing that needs the heat is stealing it from this, right? So it's not always a willingly giving. Sometimes there's an exchange. The exo, that's why it's negative, because it's losing the heat energy and it's giving it to the system that is endothermic. Okay, and we saw that very visually when we looked at the energy diagrams, because the energy diagrams for things that are endo, they go up in value because they're absorbing heat energy. So they have more stored heat energy in the end than they did in the beginning. Whereas exothermic things release heat energy, they give off heat energy. So they give away the energy that they had, the potential energy that they had stored. So how can we apply this to reactions? Well, let's take a look here. Okay, so in the case of reactions, we can't measure mass, specific heat, or temperature for a reaction, but we can if we can keep it in a contained system for whatever object either absorbs or loses that heat. So here's what I mean. Let's say we do a combustion reaction. So a Bunsen burner and a flame, right? So we know that this is exothermic, giving off heat energy. Well, where is it giving off heat energy to? Well, it's giving it off to the room. It's very difficult to measure how much heat is absorbed by the room because it's a big room. We're also in the room, so we're increasing its temperature. And so it'd be very, very difficult to measure that in any type of analytical way where we could track it back specifically to the Bunsen burner. Well, what if I change that system? And so I made it not just a room, but I put some sort of cover over it. Well, in the case of this, it's sort of a ridiculous example because so now I've got a limited space, a limited mass, I've limited a lot of things. The challenge with this one is obviously you'd run out of oxygen and it'd be a pretty difficult one to measure this way. But for a lot of our reactions, um, they take place in water. And so it's kind of easy to contain the system because now you don't measure it for the room, you can contain it within a cup. And what type of cup? So this is going to be on page number 12. You have a little picture diagram. Two styrofoam cups. And there are two because styrofoam, first of all, is a great insulator, which means that it doesn't transfer heat energy. So the heat will stay within the container and won't go out to the environment. So you have what we call a closed system. So all the heat transfer takes place between the objects inside of the cups, not outside. The reason why we use two cups is air in the middle here. So you've got air in the middle. Air is an excellent insulator as well. So you've got a double layer insulator plus an insulator in the middle. And on top of this, obviously, we don't want to leave it open to the world. We're going to have some sort of lid. And this is going to have your thermometer. Tell you the temperature. And then you may have something like, a lot of times we put like a stir bar in here so that when you put it on the hot plate stirs, this can spin. I'm kind of putting a little arrow here, not a very good arrow, but to show that this is a spinner, so not a chemical, just some sort of spinner. And you basically have two options. One is that you can start with the water already in here and add the solid chemicals in, and as they dissolve and react, then you can measure the temperature. Or instead of adding the water in, so we go back here a second, you can add the cylinders, chemical A, and you can add in chemical B, terrible graduated cylinders, sorry about the drawings, and you add them in, and they're already in solution, but the two solutions react with each other, and then they change the temperature. Okay, so either one of these scenarios works just about the same. So you say, okay, well, how can we use Q in this case? Well, we can't measure Q for a reaction directly, but we can measure it what we call indirectly. Indirectly means we measure something else and then compare it. So what we can measure for this is we can measure Q for the water. Can't measure it for the reaction, but we can measure it for the water. And since most of these solutions are basically water, because that water is either your solvent or water is what you're mixing it into, you can take the mass of the water, okay, which generally the mass of the water will be equal to the volume of the water. So we assume density is right around 1. The specific heat, we can use 4.18. And you say, oh, but Mr. Davies, some things are dissolved in it. It still usually is pretty close to 4.18. They may give you a slightly different value if they want you to use it, but it stays pretty close to 4.18. And then the change in temperature, T final minus T initial for the water, which you will have measured this with the thermometer. So it's very important that you either measure the, starting solutions in the, you can dunk it in these should start at the same temperature. So Those will give you your initial temperature, and then the thermometer inside here can give you your final temperature. Or if you're doing the one where you add the solids in, you can just measure the temperature of the water inside the cup at the beginning, before the reaction, and then after the reaction, and record those values. So in terms of a data table, the most important things that you will need to record is you will need the total volume, and you will need T initial, you will need T final, and then you also are going to have some way. Now you won't record moles, but whether it's mass or you could use grams, or it can be molarity, you need to know the moles of the chemicals that are involved. You need some way to get to moles. So whether that's grams or molarity or volume or some other way to, if it was a gas, I guess you could do the pressure to get to Pivner, but you need some way to stoichiometrically get to moles and to be able to figure out what your limiting reagent is. So these are the 4 pieces of information that we need for every calorimetry experiment to get delta H of a reaction. Okay, so if we find this for the water, how is that then going to relate to the reaction? And this gets back to the principle that positive Q equals negative Q for the exo thing. So let's take an example where we mix 2 chemicals together and they get hot. What does that tell us about our chemical reaction? Well, it tells us that our chemical reaction is the thing that is, well, we can't measure that. But if it gets hot, what does it do to the water that the reaction takes place in? It warms it up. So the water will be hot. So if you solve MCAT for the water, all you have to do is flip the sign and it will give you Q for the reaction. If you had an example where maybe your reaction is the endothermic thing, so you mix 2 things together and it is cold. So the reaction absorbed heat energy, it took it away from the water, and the water got cold, so the water gave off heat energy, okay? So if you mix 2 things in their room temperature together and they get cold, that tells you that your reaction was endothermic because it was stealing that heat energy away from the water. Water had to give off heat energy to allow the reaction to happen. But if you measure the values for the water and just again flip the sign and make it positive, that will be it for the reaction. And this assumes that we have a closed system and that none of the heat is lost to the surroundings. Any heat lost to the surroundings would be considered sources of error. Okay, so now we're going to work on a few of the practice problems on page number, okay, so we have page number 12. And okay, so it says, okay, so practice problem number 1 on page 12 says there are 12.3 grams, sorry to fix that, 12.3 grams of KNO3, and it's added to 75 mils of water. The initial temperature of the water is 23.1 degrees Celsius, and the final temperature of the water is 27.4 degrees Celsius. Okay, so again, we are not able to calculate Q for the, we can't calculate Q for the reaction, but we can calculate Q for the water. Where would water have gotten the heat to increase by 4.3 degrees Celsius? It would have gotten it from the reaction. So before we ever do any of the questions, one of the things that I think is super important to define anytime you're doing a calorimetry problem is, what is your Q endo and what is your Q exo? Because this defines how you solve the entire problem. So positive Q endo is the thing absorbing the heat energy, and what is the thing giving off the heat energy? Okay, so that has to be the reaction. We know this because the reaction was able to give heat energy to the water, which got hot. Okay, so if we look here, A says, what's the total mass of the solution? Well, if we're going to calculate MCAT for the water, right, because the one that we can solve is the water. This is the one we can solve right here. And we can plug it in for MCAT. We need a mass, we need a C, and we need a delta T. So one of the things with this is that we can't just say it's 75 grams because we have 75 grams of water. But if something is dissolved into the water, that means it's going to add mass to your total solution. So we're going to add in the mass of the solid because that adds mass to the water. So then this would be 87.3 grams. And this is your solution total. And a lot of times we call this Q and a water over here, but probably the more appropriate term is really the solution because it's not pure water. It's not pure distilled water. It's just mostly water. Because if you have a solution, it's mostly made up of H2O. So we can use the values for H2O. So, okay, this is our total mass of our solution. Part B says, what is the Q value for water? And really, we shouldn't say what's the Q value for water. We should say what's the Q value for the solution. So our Q for our solution or our water is equal to the mass, which is 87.3. Specific heat, it tells us in the problem to use 4.2. Since it's mostly water, that makes sense. And then the change in temperature. So T final is 27. This is not the world's best handwriting here. 27. 27 point, let's see, 27.4 minus 20, minus, no, let me write this very nicely here. Minus, and I might be running out of room for you to see, but it would be 23.1, and I had written those here. Okay, and then close parentheses, and then I'm going to put this into the calculator, and we're going to define Q solution. One of the best parts about the AP is they often break down the problems. So they ask you, they don't just say calculate delta H for the reaction. They ask for these steps along the way. And I'm going to plug this into the calculator and bring back an answer. Okay, so I put it into the calculator and I got 1,575 joules, or if you want to convert that into kilojoules, just be careful what they ask for. And I put a sign for these no matter what. So even if it's positive, I put the positive sign in there. Okay, well, let's take this and let's translate this to Q for the reaction. Well, where did water get 1,575 joules from? It got it from the solution of the water, got that reaction, it absorbed it because the reaction, the chemical reaction, lost it. So all you have to do is flip the sign. This becomes negative 1,575 in joules, or if they want it in kilojoules, you can write the value as negative 1.58. And just read the problem because they often tell you which units to report it in. But just remember, when you put something into Q, if you're using that equation, you get out joules because the specific heat is in joules per gram degree Celsius. Okay, so now we have a Q value for our reaction. This is Q for the reaction. Okay, and how do I now take this, which is only for this specific scenario under these specific conditions in this specific cup, and turn it into something for an entire reaction that I can use anytime? So if I use a different number of grams or a different setup, how can I take this and turn it into an intrinsic property? Well, we know that intrinsic properties are based on per values. They're fractions, they're proportions. So right now I've only got joules. So I could make this joules per gram. In most of the cases, they want for delta H for reaction, they want the units to be, most of the time when you find these, you'll find that they are delta H for reactions. Units for these are kilojoules per mole. Okay, and this mole will be the mole of whatever your limiting reagent is. Well, in this case, you're only adding one thing to water, so that's automatically your limiting reagent. Water is obviously going to be in excess since it's your solvent. So we need to figure out the moles of the KMnO4. So if we had 12 grams of KNO3 times, okay, we need to use the molar mass to convert it. So the molar mass, I'm using the rounded values, which should be pretty close in this case. So 101 grams per 1 mole. Grams cancel, so we do 12.3 divided by 101. And that is going to equal 0.122 moles. And so now I have my mole value, and I have my kilojoule value. How do I turn this into an intrinsic property? In any case, I would take the two values and divide it. So delta H for the reaction, that's why we did all of this hard work, is negative 1.5 kilojoules per 0.122 moles. And so we just divide. So 1.58 divided by, and we end up getting that this is negative. Well, with rounding, it's going to be 13.0 kilojoules per mole. Well, now if I add, I'm not sure if you guys can see that, so let me make sure I put this down here. I make sure I put the negative sign because there's always one point in it just for getting the sign right. That is my final answer. And if you could see it over there, it's the same number. I'm just not sure off to the side there. You can see it. So I'm going to continue with part 2 of this video, which is going to go over an example where you have two solutions mixed together. So page 13, number 2 in the practice problems in the next video. Thank you for listening.